Hello guys, welcome on Tesla Adventures. From today onwards, we are starting this semiconductors, and this is purely due to the upcoming JEE mains exam. And I think in around 12 days, I'll be completing the semiconductor lectures, which is for JEE, and I am just in the process of starting each chapters, and I'll be starting waves and fluids soon, and I'll be completing all the incomplete chapters within some time in the upcoming days. Okay, so this is in this first lecture of semiconductor, we are going to discuss the basics of semiconductor. So as you can see from the name, that semiconductors are the materials which have the conductivity in between the conductivity of conductors and the insulators, which means that the conductivity of semiconductors is less than that of the conductors and it is greater than that of the insulators, and it is in the range of 10 to the power minus 5 to 10 to the power 4 mho per meter. Now, the second thing is the fact that why do we need semiconductors? Some students ask that why do we need semiconductors? We can say that obviously we know that in many electrical circuits there are too many resistors, capacitors, and more electrical elements like inductors. So, in the heavier applications, that circuit which is loaded with these circuit elements becomes so bulky so that we could not feasibly use that circuit in that application. So, to avoid the bulkiness of the circuit, we are now using the integrated circuits, and this is a revolution in the world of electronics. As you know, that in a small uh, very small chip, you can integrate a large amount of programs and memory data cards, so you can operate your complete computer applications from your smartphone. So this is possible due to the integrated circuits. So in integrated circuits, we can integrate many resistors and capacitors in a very small area of millimeters, and it is done by semiconducting materials. And I can tell you that resistance and capacitance and inductance are also formed in the other way from the use of semiconductors. So this is the use of semiconductor. Now, conductivity of semiconductors can also be this is a very important aspect and advantage of semiconductor, that you can control the conductivity of semiconductor by controlling the doping amount. So we'll be studying the semiconductor, that will be studying extrinsic semiconductors. You must have also heard about the extrinsic semiconductors. So in extrinsic semiconductors, you will be getting to know that we can control the amount of free electrons in the semiconductor by controlling the amount of doping which we are doing in that semiconductor. Now, doping means adding external atoms like phosphorus and silicon crystal. So we'll be studying this in detail in extrinsic semiconductors, but the most biggest advantage of semiconductor is the fact that we can control the conductivity and resistivity of the semiconducting material by controlling this amount of doping impurity which we are adding in it. Okay, and the temperature coefficient of resistance of semiconductor is negative. It means that if we increase the temperature of semiconducting material, then its resistivity decreases. Now, we have already studied in conductors that when we increase the temperature of the conductors, then the kinetic energy of the free electrons increases, and they try to move here and there in very high speed, due to which they collide more frequently with the other electrons or atoms, and they lose their kinetic energy, and they experience some hindrance in their motion. in the process of running here and there. So due to that hindrance, we can say that the resistivity of the conductors increases on increasing the temperature. This effect is also occurring in semiconductors, that when we are increasing the temperature of the semiconductors, then the kinetic energy of the free electron increases, and they observe more and more hindrance in their motion, and therefore their resistivity increases. But there is another effect which increases the conductivity on increasing the temperature in the semiconductor. In this effect, you know very well that mostly electrons are bonded with covalent bonds, and we can say that those are valence electrons, and valence electrons could not participate in the current conduction in the semiconductors. But as we increase the temperature, the kinetic energy of those electrons increases, and they break their bonds, and they comes out of the valence band, and they break their bonds to get free, and now they are available to take part in the current conduction. So due to due to the jump of one electron from valence band to conduction band, a hole is also formed, and I'll be telling you in the later part of this playlist that what are holes, and how holes are also participating in the current conduction in the semiconductors. So by jumping of one electron, two charge carriers are formed, so conductivity increases to multiple times by increasing the temperature. So by one effect, we know that on increasing the temperature, resistivity is increasing, and by other effect, on increasing the temperature, conductivity is increasing. And when we superimpose these two effects, then we can conclude that the much bigger effect is the increase in conductivity, and therefore the net effect is the fact that on increasing the temperature, conductivity of the semiconductor increases and resistivity decreases. So this is a very important thing. And if we talk about the types of semiconductors, in many people I have asked that what are the types of semiconductors. So those kids answer me that semiconductors are of p type, n type, intrinsic, extrinsic semiconductors. This is also correct, but when I ask you that how many types of humans are there, so we cannot answer that there are Hindu, Muslim, Sikhs, and Isais, but we has to answer it in fundamental way. So in fundamental way, we can say that there are two types of humans, which is male and female. So in the fundamental classification, I can say that semiconductors are of two types. First is elemental semiconductor, and the other is compound semiconductor. Now the elemental semiconductors, which are also called as intrinsic semiconductors, are the purest semiconductors, and these are generally group 14 elements like silicon, germanium, and carbon. So in these type of semiconductors, there is no doping, and in compound semiconductors, we make a compound by mixing more elements, and these are of two types: organic semiconductors and inorganic semiconductors. The example of organic semiconductors is anthracene doped thiocyanins, and example of inorganic semiconductors is gallium phosphide, gallium arsenic phosphide, and indium phosphide. These are the example of inorganic semiconductors. Now, if we move forward, and now if we discuss about the energy bands. So let us take an example that I have taken a silicon crystal whose atomic number is 14, and this is the configuration 1s2, 2s2, 2p6, and this is hybridization 3s2, 3p2. And let us take the quantity of silicon as 1 mole. So we can say that almost there are 6 into 10 raised to power 23 atoms present. We know that the outermost shells are 3p and 3s, and these are the inner shells. And we know that at room temperature, the interatomic distance between the two atoms of a crystal of silicon is around 2 angstroms. So we are considering a imaginary scenario in which we have taken those atoms very far away from each other, and this distance d is almost the 4 times of a. So in this scenario, these two atoms are very far away from each other, and their energy bands are not overlapping with each other. But when we decrease and we can say that the energy of all 10 to the power 23 electrons is same in 3p orbit, and similarly for all 10 to the power 23 electrons of 3s orbit, the energy is same. But when we decrease the distance to c, then we can see that their external energy levels becomes overlapped to extent, and therefore due to this overlapping, there is a region which is obtained in which electrons are found, and in this gap there is no electron is found. Now, if we further decrease this distance from C to B, then we can say that all the bands are overlapped, and we can say that between the minimum energy of 3s and between the maximum energy of 3p, at all energy levels, electrons can be obtained. And when we decrease the distance further to the actual distance, which is the A, and which is around 2 angstroms for silicon, then this overlapping increases, and due to this overlapping, the some electrons which are absolutely free and which are of higher energy get separated, and their energy band is named as conduction band because those electrons take parts in electricity conduction. And the electrons which are bonded with covalent bonds are separated below, and they are represented by valence band because and they are represented below the conduction band due to the fact that energy of valence band and valence electrons is less than that of conduction electrons. Now, there is a significant amount of energy difference between the highest energy of valence band and the lowest energy of conduction band, and this energy difference is called as forbidden energy gap, EG. So this is the formation of energy bands in the solid, and we know that energy bands, solids can be of three types on the basis of their conductivity, which we can say that they are conductors, insulators, and semiconductors. So in insulators, the forbidden energy gap is so high so that it is very difficult for valence electrons to break their bonds and to jump into conduction bands. Now, breaking the bonds and jumping to conduction band means that the electrons is getting sufficient amount of energy to break the bond and to get free. So any free electron is represented in conduction band, and any bonded electron is represented in valence band. There is no such bands in the crystal. We are just representing the electrons on the basis of their energies. So for this insulators, the number of electrons in conduction band is very low, and it is very difficult for electrons to jump from valence band to conduction band. So we can say that diamond is the example of perfect insulator, and the forbidden energy gap of diamond is greater than 3 eV. Now, in semiconductors, this energy gap is less than that of insulators, and for germanium it is 0.7 eV, and for silicon it is 1.1 eV. These two data are to be remembered, and we can say that it is comparatively easier in semiconductors for electrons to break their bonds and to jump in the conduction bands. And in conductors, almost all the electrons are free, which means that in conductors, these two bands overlap with each other, and forbidden energy gap is almost zero in conductors. So we can say that these are the energy bands and in the next video I'll be bringing the intrinsic semiconductors completely. This was the introductory video of semiconductors, and in the next video we'll be bringing intrinsic semiconductors completely. You would be getting the videos of semiconductor on the daily basis, and till it gets completed I'll be uploading the semiconductors only. Thank you.